PLCs. And let me talk directly, get my pointer here. There you go. Okay, so the first one talks about what a programmable logic controller is. What is a programmable logic controller, Adam? And the other one will talk about how to program these PLCs. And I'll show you, again, you guys have done that with us. I want to remind you, you will be doing it next semester, programming and all this stuff. So that's the topic for the day, guys. So we're going to list the principal parts. What are the major parts of PLCs, of programmable logic controller? You're going to hear this all the time. When you guys work for any manufacturing floor, we're electrical designers. So remember, we build power system and lighting system and low voltage system for buildings. But if you end up doing a process control like manufacturing, you'll be involved, you could be involved in some control wiring. And I get calls all the time, Matt, for people to do some drafting for all these PLC ladder diagrams. You're not familiar with them yet, but you will be. So that's where we fit as a designers. You can make a lot of money, Derek, just doing the control part of it. It really is, design or installation. We'll talk about the difference between your computer that you're dealing with and the PLCs. Both of them, guys, have microprocessors. Matt, I'm sure, and Adam, I'm sure Scott told you guys when you were doing with S7200, that one, that's a computer. I have a microprocessor inside it. Has a lot of power, as powerful as that laptop in front of you. Okay, so that's what we will talk about, guys. This does the difference between the input-outputs. So the component is something called IOs, the input-output tracks. That's the eyes and the ears of the laptop. And then there's the central processing unit. That's the brain of that computer. It's called CPU, central processing unit, have microprocessor in it. And there's something called the program loader. This is how you program the PLCs, the programming way of the PLCs, right? An interface to put load in it. So really between the input-output, the microprocessor, which is two input-output devices, eyes and ears and legs and feet of the system, and the programming, three, you have the three major components, guys, of your PLC system. The three major components of your PLC system. We will show you guys input and output devices, diagrams for input and output devices, and how to control a process in a second. Okay, so this slide, guys, will tell you what's the difference between the laptop that you have, Karen, in front of you and a PLC. They're with said they make them. PLCs are meant, guys, for manufacturing. Where did you guys go with the tour with Scott? Did you go to the brewery where they make beer? Did you go to this place? Did you do any tours with him? Have you ever been in a manufacturing floor where they have a wall like this full of PLCs that control all these processes? You know Kraft, the cheese Kraft. I believe in Sleepy Eye, they have a huge plant there. So I did training for them and gave me a tour. It's unreal. All what they do is they take that milk, process that milk, and make cheese, different type of cheese. And you enter a room like this full of computers, as well as PLCs that control the whole process, from the dumping that milk and processing it and cleaning it and what's not, into making it cheese and packaging it. And so that's a whole process, all controlled by Allen Bradley PLCs. So the difference between the PLCs and the computer that you have, guys, they can handle a high temperature and shock and vibration. They're meant to be, for the most part, they're meant to be in a harsh environment, a manufacturing environment. So they make them a little bit more robust. Not like you can throw them out the window from the second floor, but they're more robust than my laptop and yours. Does that make sense? More robust, they can handle more vibration and shock and temperature. They also have more capability of handling the spikes in the power lines. What they do, Karen, on the inputs of these devices, they have filters where if there's spikes in the system, it filters these spikes so it doesn't alter the outcome of this PLC. The last thing when you do, guys, is you get an input to the PLC, and because of a spike in the line, it shows in the PLC as an output. So open that valve and it shows close that valve. That's disaster from a process control. So they filter, you're going to see how they filter the inputs. A lot of filtering, and also since they can corrosive environment, they can handle corrosive environment, oil and dirt. for the most part, most of the ones they have seen, guys, they put them really in a clean rooms for the most part and in a better area, but they are meant to be more robust. They're more robust computers. Think of them this way. Any comments, guys? Any questions about PLCs? And their job is to control the process. When we went to Allianz, guys, and we looked at their data center, the laptops that we saw, these are different than PLCs. They're more kind of softy ones. They sit in a clean room. Did you see how clean and cool that room that they sit in? Beautiful, clean room, cool all the time. These are not that laptop, that PLCs that you're dealing with. PLCs can be in a rough, warm, a little bit hot, meant to handle all this change in weather. Okay, so that's the difference. The major component of PLCs, Adam, these are the four major components. The first one is the power. So power supply. So you get the 120 power supply or 277 power supply to these PLCs, and you convert it to 5 volts or 24 volts so you can power the electronics of the PLCs and use these voltages as control voltages. That's the first one. The second one is number 2, guys, is the CPU. CPU is the brain. Inside your computer, you guys didn't do, every computer have something called microprocessor. A microprocessor is chips, tons of chips of electronic chips, basically little boards of electronic that cooks and converts all the inputs and outputs into logic. So the computer, basically a microprocessor inside the PLC. So every PLC have a computer inside the microprocessor called CPU, Central Processing Unit. Then you need like where's your CPU, Karen? Here's my CPU right in my head, right? Your brain is your CPU, right? For a human being. So I always compare it to a human being. Our CPU is in our brain, right? And then now your brain is worthless unless you have the inputs, the eyes and the ears and the senses, our senses, and outputs. You can kick with your foot and hands or your head and what's out, what's not. So you need the inputs and outputs to brain system. So number 3, my friends, is the inputs and outputs. These are the eyes and the ears and the legs and the hands of the CPU. Without that, the brain will not be able to implement the decisions that the brain make unless you have inputs to get data into my brain, like my eyes and ears and smells and what's not, and outputs, my hands and my legs to get things done, right? So that's exactly like the PLC. Built there almost, whoever thought about it thought of us. Everything is built after human being or birds or what's not. And the last thing, guys, number 4 is you need to be able to program it. Unlike you and I have been programmed by the Lord a long time ago when we were born, these PLCs, guys, we need to sit them. There's a software that comes with them, and you have to program it to do whatever you want it to do. This will be also on test number 4, just FYI, guys. They will tell you, there's a question from now. They'll tell you, what are the 4 components of a PLC? Done. You're looking at them. You need a power supply 120 to power it. You need a CPU so it can the brain of that system. You need an input-output device, the eyes and the ears and the legs and the hands of the system. And you need a program loader, which is basically a screen with a keypad where you can program the system. So any comments, guys, about these components? Adam, makes sense? These? Okay. Now we're talking about each and every one of them, guys, at a time. So the power supply, the first thing, the power supply takes the AC, reduce it. So the job of it is to take the AC, which is say 120 volt. It will reduce it to a desired voltage, lower it, then rectify it to DC because the system is working on DC, and regulate it. So it take the 120, guys, it reduce it to a lower voltage, convert it to a 24 volt or 5 volt, and regulate it. Make sure it stays 24 or 5. Okay, most PLCs operate at either 5 to 24 volt, between 5 and 24 volt. These are the voltage operation the electronic will work on. The voltage that when you put 5, you have to have 3 spikes. And regulate it to 5% of desired value. You have to regulate it, so you can't have, Karen, you can't have, if you're getting at 5 volts, 5 volts means 1. Every time you have a 5 volt in the logic, you guys did logic analysis, right? What do you call them? Adding zeros and ones. A 5 volt will get you 1. A 0 volt will get you 0, the number 0. Then you can add them and multiply them. And divide them and get you all these programming of that machine. So it's so important, the regulated voltage, to get you, when you get 5, you want to see 5. You don't want to see 3.5. You know what I mean? You need to see the 5 in order to know that there is an input coming to the PLC. Any comments, guys, about the power supply? Power supply take AC to DC on a form of 5 volt to 24 volt to use it as a signal and power the electronic inside it. So because you're going to be running at it. Now, you get that 5 volt and 24 volt current that you converted and you put it across the CPU. Your CPU is nothing but a microprocessor chip. It has tons of integrated circuit electronics. Transistors and resistors and capacitors. Did you guys do electronics? Yeah, you did electronics in the first semester. So remember that transistors and resistors and diodes, they put literally millions of them in a chip, 2-inch by 2-inch chip, and these millions will rectify something or it makes a certain function. That's your microprocessor. Allows you to add and multiply and divide numbers and combine them together logic. Do all the and or. Remember these and or that you guys did? And you all know you didn't do it, but you can add an or and what's not a nor. Allow you to do all these logic functions. Perform all the logic functions. That's what the job of the processor. It is a PC. It is a laptop. Your computer, a microprocessor or CPU is a laptop. You can actually talk to it through your laptop, or you can talk to it through a loader and what's not. Okay, so that's basically what the CPU, the brain, the one that's going to make the decision, analyze things. And then we have a plug connections. This is where you bring the inputs, where the I/Os, they call them I/Os, guys. The inputs and outputs are tied to the brain. Here's my brain. I need my eyes to tie to the brain. My ear is tied to the brain. My nose tied to the brain. These are the terminals that where you tie the inputs and outputs. You're going to see them in less than a second. Very simple, guys. Brain, eyes, ears bringing the input, and hands sending signal to the brain, so it can does action. Okay, so then you can test the programming, guys, using and store that program. Use some, if it's big tapes or disk or CDs or whatever. So you can program, you have the programming terminal. Don't forget there's also programming terminal where you need to program it. And you bring the input, output, you program them, and you can store the program on a CD, or most of them right now, guys, is all networked. So when you have a process that you take a cow from the east entrance of the building, canned beef from the other end. And in between, you can imagine, you can visualize what happened, right? That's what a process is. Or steel from one part of the ending, from one side, and a car from the other side. That's what a process, a huge manufacturing process. In between, guys, you need to be able to program that process. And the last thing you want to do is lose the program, right? So they store these programs. So if something happened, they can reload the program. They can adjust the program and what's not. Did you guys, you did some programming with S7200 and logos, and you will be doing that one. Adam, you did the S7200, you did the logo. Did you do the HMI too, the touch screen with us? The one the HMI that you touch the screen and turns things on and off. I don't know if you guys did that one. Did you? Okay. So that's what that's the programming. And you store, and I don't know if you guys did that, but when you're done, if a Scott asks you to give him a copy of your program, or you kept it in your laptop, exactly like you do with me when you guys do Revit, right? You have a copy. You give yourself a copy. Why? Because you don't want to lose it. After you print, you keep that copy for yourself. Same thing for the PLCs. Okay, so that's the CPU, the brain. Then we have something called programming terminals. That's the input that you program the system with it. Used to, what does it do for a living? Program that CPU and also troubleshoot the CPU. So you can program it and troubleshoot it through that so-called programming terminal that could be built, a screen guys built into the system, or a laptop attached to the CPU. I think with S7200, we had the software that we have right now. You guys download it, right? Were you using it wireless there, Derek, with us? So you can wireless log into the machine and turn things on and off and program it, download, upload your software into the S7200. Some of them are handheld devices, different manufacturer guys, with LCDs, a screen, or LEDs to do the program and show it. Others, you can have a notebook, which we do here, or a laptop, a notebook or a laptop. So you can do the programming with handheld device, little device, you plug it into your machine, program it, load it, upload it, troubleshoot it. You see them all the time when they go in the field. Or in this day and age, laptops. You grab your laptop, plug it into the machine. You can look at the programming, load the program to the machine, to the PLCs, download the program, troubleshoot the machine, turn things on and off from your laptop. I don't know, Karen, if you guys were able to click, like S7200 has the capability of as you program it, you can click on close a contact and it will run the machine right from your laptop. I don't know if you guys done that with the Scott or not. So you can run the equipment right from your laptop, in addition to troubleshooting it and programming. Any comments, gentlemen? Any questions about that? Comments, questions? What's in it for you guys? You're going to be a project managers, right? And you're going to be a designers. You walk into the field, it's good to know a few things about these systems, and you might branch and become a control designer. I have a lot of calls, guys, for people like yourself to do control design. All what you do then, you don't do lighting and power like we did with Chad. All what you do is just contacts and relays, like you're going to see in a second. And there's money to be made. Okay, here's the programming, guys. We'll talk about programming in a second. Here, this is a coil inside the PLCs, and all these are inputs and outputs that's driven by internal or external. Same thing, coil. You always end up at inputs. These are typically inputs, not outputs. These are your ins. All these are ins, and these two are out. The O's, input outputs. And you're going to see how we're going to program it in a second here. When you program it, the PLCs, guys, through the terminal. My God, there's the software they use. S7200 has a software. You're going to be using it. You guys have used it, and you grab these graphics. Do you guys remember Dirk grabbing these graphics on the screen and putting them together and connecting them to program? Karen, do you guys remember that? You didn't like it that much. The PLCs, no. Okay. Stick with the power. So when you grab them, you can grab a contactor. This is normally open contactor. That could be an input. When it closes, it gives a 5-volt signal. So, hey, do something. I am giving you the green light. This is the opposite, of course, normally closed. This is the coil. When you energize this coil, it gives you an output design. And these are how you connect them together, down run and closed run. You connect these together. Adam, do you guys remember doing these with us graphically with S7200? I hope you remember some of it anyway. I can't emphasize, guys, that's in addition to knowing the power and lighting and low voltage design. This is the control design. This is process control. And Matt, if you like computers, I don't know. Some people like it, some people don't, but it's another option for you. Okay, so now that's the programming. We do the programming with the language. You're going to see in a second. Then we need to, after you program the PLCs, the brain, you needed to do certain things, guys. So you need the IOs. We call them IOs, input output racks. You need input output racks. These are this is their job. Connect the CPU into the world. These are the eyes. You have to bring the inputs, the eyes and the ears and the senses of the system, and then the hands and the legs of the system. So it implements the program. And then the input modules will carry the information from the sensing devices, temperature, flow switches, into the CPU. So if the temperature in this room, guys, goes higher than a certain value, a thermostat will send a signal to the PLCs. The PLCs will say, yeah, when I get this signal, I'm going to go ask the air handling unit to start throwing more cold air in this area. So the inputs take sensing devices, physical, mechanical, sensing devices, get the inputs from them into the PLCs. These are the input devices. You're going to see them in a second. Now, what's the output? The outputs are the legs and the hands. You need to implement the orders. So you get the output instruction from the CPU into the devices. Now, Adam, the room become very hot in this room. The thermostat here sends it. That's your input. It sends the signal to the PLCs. The PLCs program, when you get that signal, the 5-volt signal, what are you going to do with it? Okay, now you program it to say, when I get it, send the signal to Mr. Air Handling Unit, right? That's your output. Send another contact, close another contact that start the air handling unit to dump more cold air in this particular room. So that's basically what your PLC is. I/O racks, input-output devices. Any comments, guys, about the input-output devices? Input-output devices, eyes and the ears and the legs of the system. Really cool. You can't live without them. The capacity, guys, how many IOs you need? Well, how many systems you need to control? If you're bringing a cow from the east side of the building and canned beef from the other side of the building, you need a lot of input outputs in between, right? Canned and cut and chop and get rid of all this good stuff, right? Fully automated system. If you have a fully automated system, you need a lot of inputs and outputs, sensors everywhere. So the size of the PLC will determine the size of the PLC and the cost, the input-output devices. PLC is being intended to handle, you can have 16 input-output devices, that's a small system, or thousands of input-output devices. They are on a rack, guys, so what they do, you don't have to start with, you can start with 16 input-output devices. As you grow, your company grows, you start plugging more input-output devices in the same PLCs. So that's the nice thing about their modules. You put them in a rack and you can start plugging more input as you need. You start with 16 and then you need another 16, you plug another inputs and wire them into the PLCs and program them. Large PLCs have, like I said, several hundreds of input-output devices. And of course, the more input-output devices you have, the more the processor speed. Computer. The more you have to put things into the computer, it will affect the speed, but the computers are very, very fast now. They can handle a lot of stuff. And the amount of memory, of course, you need to have memory in the CPU. So there's a happy medium between if you have this PLC can handle this amount of input-output devices. If you go higher than that, you have to go at different levels of PLCs. Any comments, guys? Any questions? So when you build your PLC system, and not like you would probably do, guys, you probably will need a lot of training to do that one. Keep in mind in how many input-output devices will decide what type of PLC processor you're going to have. Okay, so then we go into the input devices. So these are the programming input-output devices. The input devices, what they do for the input device, you're going to see, guys, in a second. Up to isolation. Anybody have heard that term? Up to isolation. What they do is electrically separate the incoming signal from the CPU. Now you need a signal coming from a sensor. That signal could be corrupted. If you bring the sensor to the CPU, you're going to burn your CPU or get it wrong distance. So what they do, you're going to see in a second, guys. They convert the signal into light. And then convert the light back into digital, electrical. So they isolate them by a light. You're going to see it very, very simple, very easy. When the power is applied to the circuit, an LED turns on. So what they do, you have an input atom. When you get an input, an LED turns on. There's a sensor here, a photosensor. It sees the LED goes on. It sends the light, no electricity, sends the light, and turn and give a signal to the PLC. They say, hey, we got a signal, do something. So they isolate them via something called up to isolation. Smarter than Chad, believe me. So that's how they isolate them. The light is detected by a photosensor, which signals the CPU there is a voltage in the terminal. Look how they do it, guys, right here. So, all right, thermostat right here, right? Thermostat got 24 volt here. We got, in this case here, we got 24 volt here AC. Let's just say AC. Coming in, we convert this 24 volt, guys, into 5 volt DC. Can you guys see? Remember that bridge that converts AC to DC? Full rectification. You rectify the input into DC. You put a current limiting resistor, Karen, and then you put that 5 volt into a diode. Now the diode makes light here. Can you guys see that? And when the diode makes light, that light will be picked up by a transistor, a phototransistor, and then the phototransistor will give a 5 volt DC into the CPU. Any comments, guys? Any questions about how the input is isolated from the CPU for safety? One more time, Adam. You bring the 24 volt signal, you convert it into DC, and put it through that circuit. The circuit will power an LED light. The LED light will be sensed by a phototransistor, and the phototransistor, gentlemen, will convert this into a signal that comes inside the CPU as a 5 volt, which converts into the digital number one, which is, go ahead, we got an input to do something. Any comments, gentlemen? Any questions about this? Comments, questions? This is probably the heart of how we do the input module, how the input module work. And Karen, all this will be inside the CPU, the input module, and the only thing you guys can see is right here. Just you tie to the input. So Adam, when you were tying the input to the S7200, that's what you were doing. You're tying there. Everything else happened inside the system. Okay, output devices. The same thing, guys. Line isolation between the output. You have a line isolation between the external circuit and the CPU. You're going to see it, and you can do it in two ways. You can do optical isolation with LEDs. LED signal a solid state device to connect to the load line, or you can use a small relay contacts connect the load to the line. Two ways. You're going to see the picture. Power, and then the equipment that you want to power, the equipment that you want to start, it has its own power. All what you're doing is just closing a contact for it, and it will power. You're going to see, guys, when we do the programming, it's easier said than done. This is how it looks like. So here I got here's my CPU. I got 5 volt here, 5 volt DC inside the processor. The processor put 5 volt here. It's a diode. An LED, what does an LED, you put 5 volt across an LED, what does it do? Lit. So you have light, now the light comes out of this. Now when the light comes out of this LED, this is logic number 1. We're getting an output. This will be sensed by photosensor, okay? It's a relay, photosensor. It senses it. When it senses it, guys, it closes. Can you guys see that? It shuts down. And I have 120 volt coming in. And now, guess what? This relay is on. It turns the relay on. So this triac, guys, act like a switch. Like the transistor, exactly like a switch. Instead of manually opening it, it senses the light came. When it picks light, it closes. That's what it means. Transistor, since the voltage, it closes. When it closes, it brings 120 volt into the coil. Now, what this coil can do with the 21 volts, you know what they do with that? They put it into a contactor here. Here's my contactor, and you can run a 300 horsepower motor. You see that little coil, a 120 coil they closed from the PLCs? Now, this coil will go bam, 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 shut this contactor and start a 300 horsepower motor. And all came from what? 5 volt coming from the VFD. Converted into a light, picked up by this triac, closed, bring the 120 into a coil. Coil is energized, and the coil will drive these contacts to shut. But can you guys see the isolation, the light isolation? They isolate the output circuit from the CPU for safety. So that's what you have. Any comments, guys? Any questions about the input? Can you guys see where the input has isolation and also the output has an isolation? You're going to see a better picture in a second. Any comments? Any questions about input outputs? Input outputs. So very, very cool the way it works. Then we have internal relays, guys. The nice thing about PLC is instead of building relays, like if you don't have PLC, every time you have to close and open a contact, you have to have a relay. Relays and timers and counters can be virtual devices inside the PLCs. Isn't that what Scott told you guys when you walked into his lab? He said, the beauty of a PLC is you can create as many, for the most part, as many relays and counters and relays, counters, and timers as you want. So we have performed these. What do? They perform an actual logic for control circuits. They are, I can't emphasize the word. Can you guys listen to this word? This is called imaginary devices that exist only inside the computer. There is no timer. If you have a PLC, there is no real timer, right? They all sit and exist inside the computer, the timers and the programmers. And they have charts with numbers. The manufacturer has charts with numbers that you can use for the timers and the internal relays and what's not. Input outputs used to program. Some will use with input outputs, internal relay coils, and timers and counters. So they give them certain timers certain numbers, guys, that are associated with the input output devices, relays and counters and timers. Any comments about internal relays? So you're going to see a lot of stuff later on in the second chapter, guys. They're all these relays don't exist. They are hypothetical relays. They're imaginary ones. That's the beauty of PLCs. Do you guys know the PLCs was invented by the auto industry because they keep changing every year. They have a new model. They got sick of wiring and rewiring things, right? So what they came up with the PLCs where you don't have to wire and rewire. You just change the program and they make it make different type of cars for the most part. Okay, timers and counters. Same thing. Timers and counter guys are all internal relays. No physical presence for these timers. They don't exist. They're in the memory, in the logic. Difference with other relays, number of counts times delays must be programmed. All these, the timers and the counts, all programmed, so they don't exist outside the system. And their timers go in increments of 0.1 seconds for the most part. When you have a timer, I want to, you're going to see in a second, I have an example for you guys, where I want to start this machine after 5 seconds. So you click a timer, 1, 2, Mississippi, 2, 3, 4, 5 Mississippis, the machine will start. Where does this timer exist? None. Where? It's in the brain of Ch, which is the CPU. That's the beauty of the of PLCs. You don't have timers. If you don't have a PLC, you know what's going to happen? You have to have a big device that's called timer in order to get this to work. Okay, so we have the off delay and on delay. I'm sure you guys off delay. You delay the off or you delay the on. When you put your timers, you're going to see, so you turn off the system, and after the system is turned off, 10 seconds, do action. So these are the programs that you can do. We'll see them in a second too. Installing programmable logic controllers. So the rest of it, guys, so we have is just installing them. Keep the wire runs short as you put your conductors. I'm sure Derek, Scott told you guys, you don't want to put more wires in the circuit, in the input-output than you need to, because of capacitance and what's not. Land out of the signal cables, use shielded cable because of interference, ground the chassis of the system. So all these are methods. Isolate the circuits from the power circuits. You don't put them in the same conduits because of induced voltage on them. So here's your shielded cable that you use so you minimize the interference. You cross the power line with a right angle like this, so you don't have induced voltage into the shield. Then you minimize the induced voltage. The last thing you want to do, guys, is you have a power line here and a control line next to each other. So Adam, what happens if you have a shielded cable next to a power line that carrying 500 amp? That 500 amp is a huge amount of energy. It will induce noises. Corrupted, it could corrupt the data. It will corrupt the data. So that's a few methods. The other thing, guys, you have to also ground the track, the input-output track. Everything is connected to the same, and the sensors, everything is grounded to the same point. Everything is grounded to the same point, so you don't have a voltage difference between them. Okay, so we ground them, we keep them short, we isolate them from the power, unline the cables, guys, and we shield them. There's something called induced noise. A noise is a term for corrupted data. They call it noise. The smarter than Chad guys use differential amplifier. You heard this one built inside the PLCs. What the differential amplifier, Adam, does, it takes the signal that you want, and if there's any noise on it, it will get the noise out and amplify the signal. What's the signal? My voice. So if I have my voice, I want to amplify my voice, the signal. And there's noise around it, it will isolate the noise, dump it, and only picks my voice and amplify it. Who cares? You guys probably, we don't, unless you're a control engineer, this is huge. This will guarantee you that your system is not going to malfunction, or will give you an indication it's not going to malfunction. Okay, detect the voltage difference between a pair of signal wires, and ignore the noise, isolate the noise, and amplifies only the difference, the voltage difference. Amplifies only the voltage difference. Amplifies only the voltage difference. It looks like something like this, guys. So here's I'm just going to be, here's a signal here coming that looks like this, and a signal that on this that looks like this. Okay. Now it looks at them and it gets the noise out and it multiplies them. And it compares them together, gets the noise, which is interference out, and it amplifies only the signal that you want. And it looks something like this. Does that make sense? Differential amplifier, their job is to amplify the signal, the voice, the signal that we want, and ignore all the noises, interference. All the noise interference. Okay, so that's basically, guys, what this chapter is talking about, PLCs. A few quick reminder, guys, that PLCs, we have the power supply for the PLCs. We have the CPU, we have the programming, and we have the input-output devices. They are meant for harsh industrial environment, extreme temperature, voltage spikes, they can handle it, that's what we talked about. Use schematic and ladder diagrams to program them into the computer, into your computer. And I'm gonna show you just a couple of pictures. Okay, so let's go. We talked about these one. Okay, here's one multi-input, guys. Look at this. I have one input here. Input 1, input 2, 3, 4, 5. Can you guys see the isolation? I want to just bring your attention to this. How they use the isolation devices right here. Isolation devices before they put them into the PLC. Before they put them into the PLC. Isolation devices before you put them into your PLC. So these are 4 inputs. So I can bring an input from each and every one of these areas. And all this stuff that you see, Karen, is inside the PLC, inside the input-output device PLC, right in here. So that's my multi-input devices. Oops. Okay. All right. So here's how they do them. The programming. I want you guys to pay attention to this because that's what next chapter will talk about. Look what happened here. We're bringing an input from a limit switch, thermostat, a float switch, and a push button. All these are 3 inputs coming to the PLC, right? So when you close, look what happened, guys. When this closes, here's 120 volt here. You bring 120 volts right in here. You convert this one into, say, 24 volts right here. This will create a light. This will pick up and take 5 volts, and you put it inside the CPU. Can you see how it works? So this closes because of limit switch. Somebody pushed it to close, right? It picks up the 120, bring the 120 across this. It converts it to DC. Remember, this is AC here. Converts it to DC, 24 volt here, and then this will energize the LED, make light. This will pick it up and put 5 volt here, and the CPU will see an input. As simple as this. Same thing happened here. You close that one, or you close that one, or you close that one. It will create a 5 volt, ultimately 5 volt right inside the PLC, which is an input. Look at the output. I want to bring to your attention, guys, the common wire that they use. I'm sure you wired it, but you guys forgot about wiring it. This is the common wire between all these. They call it the common. With S7200, there was a common wire that you get tied to, all of it. Let's go to an output devices. Okay, so here's the output device is the same thing. Look, we looked at this one, guys. You put the 5 volt here. You create a light. You pick it up. Now you got yourself. You close this one. This will close. You put a 120 volt across this one. This will energize and drive a couple of contacts right in here to close a 500 horsepower motor. See how easy that is? From a light, it's sensed by a track, closes, no relay here, closes, and start the 500 horsepower. That's your output. I want to bring to your attention, guys, there's the common here, as well as you bring the voltage into the PLCs. So that's your input. You can use a transistor, or you can use a triac to do the same function. You can also use a relay. Here's a relay. You guys remember, there's also relays that comes with the PLCs. You can use a relay. A relay is very similar to the relays that we have. So you get the 24 volt here, 24 volt. You energize this coil. This will close and does the same thing. So either transistor, triac, or relay. These are typically triac or transistors are the common one to get you an output. Okay, Adam, here's all the outputs. There's multiple outputs coming from the same CPU. So if I want to, I don't know, I want something, this output, I want to put light, red light on. Red light on. So you bring a neutral here to it, and then if when it gets 5 volt here, no problem, convert it. This is well lit, this will catch, closes. My control circuit is 120 here, volt. Now the power is going to come from here, here, all the way here, and back. Now the red light will go on when I get 5 volt from the CPU. Same thing for each and every one of these outputs. Can you see these are separate outputs that you can do? We're going to see in a second, chapter 2, we'll talk about programming them. These are your outputs. And we can use timers, like I said. And then when you install them, guys, you're going to keep them in a right angle like this. You don't put them side by side because of induction. Shielded cable, grounding, amplifier. And the rest of them, guys, are a bunch of pictures that we can use to get your input-output devices. These are modules that you can use for different manufacturers. There are different modules that they use. And you guys have seen a few of them with us. So input-output devices, programming, it's computer, basically. Different chips. Here's a handheld programmer. This is a laptop. You can attach it to the PLC and program it. You can have also a screen like this. You can program it with a screen. Or in this day and age, Karen, we have a laptop where you plug into wired or wireless and you program your equipment. Input-output modules, and the electronic inside them and what's not. Okay, that's all I have about this chapter. Any comments, gentlemen? Any questions? Any comments, any questions? I'm going to give you 10 minutes, and I really would like to go to the second one. Second one is even simpler. It shows how you program a PLC. Very simple. So you're going to spend maybe half an hour with your friend Chad. Take a logic circuit, guys, and convert it into a PLCs. So shall we? All right, let's take 10 minutes, and then we'll go. Thank you.